Hello friends, welcome back to my YouTube channel. This will be part number 6 of my discussion on liquid extraction, and in this I'll be talking about ternary equilibria. I'll be talking about how to represent ternary equilibria on rectangular coordinates. In my earlier videos, I have talked about representing the ternary equilibria on equilateral triangular coordinates. So ternary equilibria can also be represented on rectangular coordinates, and we are going to understand how that can be done in this video. So first we will know how to plot the binodal solubility plot on a rectangular graph, and then after knowing that, we will understand, or I'll be discussing one numerical where you'll learn how to plot the binodal solubility curve. So let us begin the discussion. Let us first understand what is a ternary system. So there are three components. I'm going to denote those components by A, B and C. In this case, A plus C forms the feed solution, the solution from which C is to be recovered by liquid extraction, and B is the extracting solvent, the solvent used to extract C from this feed solution. Commonly, as I have told you in my earlier videos, commonly in liquid extraction, C is soluble in both A and B. C is soluble in A and C is also equally soluble in B. But in this case, and which is very common in liquid extraction, A and B, these two are also soluble in each other, but only to a limited extent. So we are considering a system of three components. We are considering a ternary system of three components, A, B and C, out of which A and C forms the feed solution and B is the extracting solvent. C, the common case, commonly in liquid extraction, C is soluble in both A and B, but A and B, they are soluble in each other, but only to a limited extent. So you can understand, and the feed solution is mixed with the solvent, and the mixture is thoroughly mixed and it is allowed to settle. After sufficiently long time, it will settle into two layers. One layer will be the A layer and the other one will be B layer. And then C will be moving from A layer to B layer, and after sufficiently long time there will be a case of dynamic equilibrium where C will be moving from B layer to A layer and from A layer to B layer, but the rate at which this happens is the same, and therefore there is no net transfer of C across the interface between the two layers. And when this happens, we say that a dynamic equilibrium is reached in this case. I have talked about this dynamic equilibrium in my earlier videos. I'm giving link to those videos in the description section. You please watch those videos. And since we have a system where A and B, they are soluble in each other to a limited extent, what is going to happen? The A layer will be containing some little amount of B in it, and therefore now we will be calling it as A-rich phase, or the other name is raffinate phase. And since A is soluble in B to a little extent, there will be some amount of A, and that's why now we are going to call it as the B-rich phase or the extract phase. The solvent-rich phase is called the extract-rich phase, whereas A, which is said to be the carrier solvent. Carrier solvent rich phase it is said to be the raffinate layer. It is the raffinate layer, and B rich phase is the extract layer. I have talked about it in my earlier videos. I am giving link to those videos in the description section. You please pause those videos if you have not seen them. Now let us know how the binodal solubility curve can be plotted on a rectangular graph. In order to plot the binodal solubility curve on rectangular coordinates, there will be two axes, x-axis and y-axis. And now we are going to learn how to plot the binodal solubility curve on such a graph. For plotting the binodal solubility curve on rectangular coordinates, what do we use? We use weight fractions of B and C. Weight fractions of B and C in the two layers, that is A ridge layer and B ridge layer. Now, how is the binodal solubility curve plotted? Let us understand. Weight fraction of B in the A ridge phase is plotted against weight fraction of C in the A ridge phase. Let me erase this so that you'll understand this. So how are we going to plot the binodal solubility curve? We are going to plot weight fractions of B in the A ridge phase, which is nothing but the raffinate phase, against corresponding weight fractions of C in the raffinate phase. So this will give us one part of the binodal solubility curve. And then how it is plotted, I have written over here. So let me tell you. So in order to plot weight fractions of B against weight fractions of C in the A ridge phase, what is done? Weight fractions of B, they are plotted on the x-axis, and weight fractions of C, they are plotted, corresponding weight fractions of C, they are plotted on the y-axis. So this gives one part of the binodal solubility curve. Then we plot weight fractions of B in the B ridge phase, which is the extract phase, versus weight fractions of C in the B ridge phase. That is, weight fractions of B are plotted against weight fractions of C, this time, and the B ridge phase. And how it is done? Again, weight fractions of B, they are plotted on the x-axis, and weight fractions of C, they are plotted on the y-axis. So this activity or this task is going to give us the other part on the binodal solubility curve. So you may have this data where you have A ridge phase, and composition of the A ridge phase is maybe given to you. Now over here I am showing weight percentage of the three components. A ridge phase, which is in equilibrium with B ridge phase, and at equilibrium you have these compositions. So you have weight percentage of A in the A ridge phase, weight percentage of B in the B ridge phase, weight percentage of A in the A ridge phase, weight percent of B in the A ridge phase, weight percent of C in the A ridge phase. Similarly, you have weight percentages of the three components in the B ridge phase. Sometimes they may just give you weights, weight of A, weight of B, weight of C in each layer. Whatever may be the case, you can convert them to, or we have to convert them to fractions. So as I said, we need weight fractions of B and C. So what we have in this table is weight percentages. So you simply divide this percentage value with 100, you are going to get the fractions. So weight percentage of B divided by 100 will give you weight fraction of B in the A ridge phase. Similarly, weight percentage of C divided by 100 weight fraction of C in the A rich phase. Similarly, you'll be getting weight fraction of B in the B rich phase and weight fraction of C in the B rich phase by dividing the percentage value with 100. Okay, so let us look at the binodal solubility curve on the tabular plot. So on the x-axis, we will be plotting weight fraction of B, and on the y-axis, we will be plotting weight fraction of C. Now, let me first talk about a point. I'm calling that point as point L. I have discussed this in my earlier video where I have talked about how to represent ternary equilibria on equilateral triangular coordinates. So the discussion over here is similar to that discussion. So let us first talk about a point which is point L, and I'm representing that point over here. Now what does this point L represent? Point L represent a rich saturated solution of A and B, which is obtained by adding B to A. So since we are talking about a system in which A and B are soluble in each other to a limited extent, and if you go on adding B to A stage will be reached where you are going to get A rich saturated solution. And why we say A rich saturated solution? Because in that solution, A is the measure component. So you get A rich saturated solution. If you try to add more B to the saturated solution, what is going to happen? The solution is going to separate into two layers. Are you understanding it? So this is A rich saturated homogeneous solution of A and if any more addition of B is done, there will be separation of that solution into two layers. So point L, it represents such a saturated solution. Then you have point K, which is over here. What does point K represent? Point K represent B rich saturated solution. B rich saturated solution of A and B, which is obtained by adding A to B. So if you go on adding A to B, you are going to get, at one stage you are going to get B rich saturated solution. If you try to add more A, then again the solution is going to separate into two layers. So it is point K is representing B rich saturated solution of A and B, which is obtained by adding A and B. Now let us talk about point J, which is lying over here. Now this point J, it is a binary mixture of A and B. But here there will be the mixture will be containing two insoluble liquid phases. So one phase will be A rich phase and the other phase will be B rich phase. The composition of A rich phase at point J will be given by point L, whereas the composition of B rich phase, it will be given by point K. Okay, so now we have understood how this 3 points L, J and K, they represent different types of solutions. So A rich phase at point J, A rich phase and B rich phase, I said A rich phase composition will be given by point L and composition of the B rich phase, it will be given by point K. Now if you go on plotting weight fraction of B versus weight fraction of C in the A rich phase, remember I had shown the data will be in this form. Let me draw over here. So you have data for A rich phase and then data for the B rich phase. And if you plot data for the A rich phase, where you are plotting weight fraction of B against weight fraction of C, then you are going to get this plot is going to tell you how the solubility of A rich phase changes if you add C to that mixture. So this plot of weight fraction of B versus weight fraction of C for the A rich phase, the plot will tell you how the solubility of the A rich phase, it changes if you go on adding C to that A rich phase. And this plot will then be called the A rich solubility curve, because it tells you how the solubility is changing on addition of C. So this is the part of the curve, or the A rich solubility curve, that you are going to get by plotting weight fraction of B against weight fraction of C for the A rich phase. Similarly, when you plot weight fraction of B versus weight fraction of C for the B rich phase, you are going to get how the solubility of B rich phase changes as you go on adding C to it, and you'll be getting the B rich solubility curve, which now I'm showing by brown color. So in this way, you get two curves, and the two curves in combination forms the binodal solubility curve. And now in this way, we have plotted the binodal solubility curve on a rectangular graph. The two curves, that is A rich solubility curve and B rich solubility curve, together they form the binodal solubility curve. So this is how you can plot the binodal solubility curve on a rectangular graph. On x-axis, you are plotting weight fractions of B, and on the y-axis, you are plotting weight fractions of C. Then, if you have to talk about a point that is lying outside the binodal solubility curve, like point S over here, what does this point S represent? It represents a ternary mixture of A, B and C. A mixture containing all the three components A, B and C, but it will be a homogeneous liquid solution of a single liquid phase. There will be only one liquid phase at all points which lies outside the binodal solubility curve, like point S in this case. Then a point beneath the binodal solubility curve, like point M, which now I am showing over here. What does this point represent? This point represents a ternary mixture of the same three components A, B and C, but in this case the mixture is separated into two insoluble liquid phases. The mixture is separated into two insoluble liquid phases. That means at all points beneath the binodal solubility curve, you'll be having two insoluble liquid phases coexisting. Whereas at all points outside the binodal solubility curve, you'll be having a homogeneous liquid solution of the three components. There will be only one single liquid phase. So at point M, as I said, there will be two insoluble liquid phases. One will be rich in A, so that is A rich phase. We call that as the raffinate phase, while the other phase is B rich phase, which is the extract phase. And these two phases are in equilibrium with each other. All points beneath the curve will represent two insoluble liquid phases which coexist and which are in equilibrium with each other. Now let us talk more about point M. At point M, the A rich phase is called the raffinate phase, as I said, and its composition is given by point R, which now I'm going to show over here. This is point R. So point R gives the composition of A rich phase that is present at point M. Then the B rich phase, we call that as the extract phase, and its composition is given by point E, which now I am showing over here, point E. So point E gives the composition of the B rich phase, which is the extract phase that is present or that is represented by point M. Then the line joining points R and E, a straight line that joins point R and E and which passes through point M, is called a tie line. a line joining points R and E, and which passes through point M. That is called a tie line. So now I have shown the tie line over here. And there are infinite tie lines on this particular ternary equilibrium diagram. We had a similar discussion when the ternary equilibria was represented on an equilateral triangular coordinates. I'm giving link to that video in the description section. You please watch that video if you have not yet seen that. And the point at which A reach phase and B reach, the point at which A reach solubility curve, the green curve, and the B reach solubility curve, the brown curve, the point at which these two curves meet, like the point which I am showing over here, point P, that point is called the plate point. And what can you say about this plate point? The plate point is the last tie line whose length is 0. Usually, this point is not at the maximum concentration of C on the binodal solubility curve. It is not present at the maximum concentration of C. And I have talked about those tie lines in my earlier videos. In my earlier video on ternary equilibria, which was represented on equilateral triangular coordinates. So in this way, we have understood how we can plot the binodal solubility curve on rectangular coordinates. What you have to do, from the given data, you have to get weight fractions of B and C in each phase, A reach phase and B reach phase. Then you'll be plotting weight fraction of B versus weight fraction of C for the A reach phase, and then you'll be plotting weight fraction of B against weight fraction of C for the B reach phase. So each plot is going to give one part of the curve, and when you plot all the points, you'll be getting the binodal solubility curve. Now let us learn how to do that by discussing one numerical. I am using the same numerical to tell you how you can plot the binodal solubility curve on rectangular coordinates. You have the ternary equilibrium data for system of water, which is A, isopropyl ether, which is B, and acetic acid, which is C, and it is given in this table. It is given in the table, and by using that data, we are supposed to plot the binodal solubility curve on rectangular coordinates, and the data is given to you. So you have water layer, and in water layer, percentage weights of each components is given to us. Similarly, data for isopropyl ether layer is given. So you have percentage weight of A, percentage weight of B, percentage weight of C for the water layer, and then percentage weight of A, percentage weight of B, percentage weight of C for the isopropyl ether layer. Now let us use this data to plot the binodal solubility curve on rectangular coordinates. So what is given to us? You have a ternary system of water, isopropyl ether, and acetic acid. Water is A, the carrier solvent, isopropyl ether is B, the extracting solvent, and acetic acid is C, the solute which is to be extracted. The ternary equilibrium data is given to us in the table. And what are we supposed to do? We are going to plot the binodal solubility curve on rectangular coordinates. So let us do that. So first of all, let us solve the numerical. First of all, we will get the required data, the data that is required to plot the binodal solubility curve on rectangular coordinates. So for water layer, I am converting percentage weight of B to weight fraction of B. How that is done? It is done by dividing the percentage value with 100. So if I do that, I am going to get various weight fractions of B in water layer. So you can see 1.9 divided by 100 is 0.019, and similarly you get other weight fractions of B in water layer. And now X is nothing but weight fraction of C in the water layer or the raffinate layer. So again, it will be obtained by dividing the percentage value with 100. So it will be 0.69 divided by 100 is 0.0069. Then 1.4941 divided by 100 is 0.0141. Similarly, other fractions you can get by dividing the percentage value with 100. Similar calculations are done for the isopropyl ether layer. First you get weight fraction of B by dividing weight percentage with 100. So 0.993, 0.989, 0.984, 0.971. Similarly, other fractions are obtained for B. Then we have to get weight fraction of C, and weight fraction of C in the isopropyl ether layer or B-rich layer or the extract layer, we denote that by Y. So this will be 0.18 divided by 100, it's 0.0018, then 0.0037. Similarly, all other percentage values, they are divided with 100 to get the fractions. So now you get all the fractions. Now what is left? You just have to plot weight fraction of B versus X for water layer, and then weight fraction of B versus Y for the isopropyl ether layer. So I have chosen this scale. So on x-axis we are going to plot weight fraction of B, and on the y-axis we are going to plot weight fraction of C. So we will be plotting the points simultaneously. That means one point for the A-rich phase and corresponding point for the B-rich phase. So this is the first point for A-rich phase, and this is the corresponding point for B-rich phase. And they are in equilibrium with each other. That's why I am going to connect that with a tie line. Similarly, the second point, it will be connected by another point. Then the third, again connected by a tie line. Fourth, connected by a tie line. Fifth, connected by a tie line. Sixth, connected by a tie line. Seventh, connected by a tie line. Eighth, again connected by a tie line. And the last point, again it is connected by a tie line. So in this way, you can further join this two curves in order to make it a smooth curve, and that will be the Binodal solubility curve. So in this way, you have to plot, or you can plot the Binodal solubility curve on rectangular coordinates. So with this, I end my discussion. At the end of this discussion, I am sure you must have understood how you can plot the Binodal solubility curve on rectangular coordinates, or how to represent the ternary equilibria on rectangular coordinates. I hope you must have learned something. If you have any doubts, please mention them in the comment section. For now, thanks for watching the video. Do subscribe to my channel. Tell your friends to subscribe to my channel. And if you have any doubts, you please mention them in the comment section. I will try to answer your questions. And to watch my videos. If you like them, please hit the like button. Also hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, thank you. Have a nice day. Bye bye.